All right, this is the second video that talks about cardiovascular and respiratory responses to exercise. It's a little longer, but I'm going to try to cover it a bit faster. And so here are some data that compare responses of men and women. All it's looking at really is cardiac output, stroke volume, and heart rate. But a question that you might ask is, do women have different cardiovascular responses to exercise than men? The answer is that if we looked at the pattern of response, if we did a line graph, that would look the same. So the shape of the change looks the same. It's the magnitude that's different. And so as you look at this, you can see that, in fact, there are some differences here. And so you can see women have lower stroke volumes, but for at least absolute work, they have a higher cardiac output. And then they also have higher heart rates. So there's some interesting stuff there. Well, why is the cardiac output of women greater than the cardiac output of men at the same absolute intensity? And it appears that the real difference really comes down to oxygen carrying capacity. And so women do have a lower O2 carrying capacity. They don't have as much hemoglobin. They don't have as many red blood cells. And so you may remember that testosterone stimulates production of erythropoietin, and erythropoietin stimulates production of red blood cells. And so men are always going to have a higher oxygen carrying capacity than women will. That means that women will have a lower AVO2 difference. And I hope that you remember the Fick equation. Fick equation tells us that cardiac output is equal to, I'm sorry, I said that wrong. It tells us that VO2 is equal to cardiac output times AVO2 difference. And so if AVO2 difference is lower, cardiac output has to be higher to make up for that. And then again, women are smaller, so they tend to have smaller hearts, and that means they also tend to have smaller stroke volumes. And so as a result of that, they have significantly lower Qmax and maximum stroke volume compared to men. And that means that they have to have a greater increase in heart rate in order to try to get the cardiac output up as much as they can. So their heart rate will go up more than the heart rate of men. When we look at incremental exercise, again, the response is the same. So if you had VO2 for exercise intensity, the line would have the same slope. It's just that it would go higher for the men than it would for the women. And if we did VO2 in liters per minute, we would see that VO2 max is about 40 to 60% greater in men. If we express VO2 max in mLs per kg per minute, you can see that that difference isn't quite as great. It's now 20 to 30% greater in men than women, and here the solid line shows you VO2 maxes of women, and this is the average VO2 max of this group of women, fairly large group, and it's right about 42. Here's the average VO2 max of this group of men, right about 55 mLs per kg per minute. Well, the next thing that these authors did was that they took out the influence of body fat, and they expressed VO2 in mLs per kg of fat-free mass, no body fat included. And now you can see that the women get even closer to the men. The men are between 0 and 15% greater VO2 max this way. Those data are showed by the dashed line. And so now the women's VO2 has come all the way up to about 54, 53, somewhere around there. The men's has gone up to, roughly 63-ish. And so now you can see that that difference is not as great as it was. And again, just to remind you, women do have significantly lower Qmax and maximum stroke volume, and that is partly because of size of the heart. They have to increase heart rate more to increase Q than men do. They have a lower oxygen carrying capacity because of less hemoglobin, less testosterone, less erythropoietin. That will translate into a lower AVO2 difference. And again, remember the Fick equation. VO2 is equal to cardiac output times AVO2 difference. So at a given VO2, the women will have to have a higher cardiac output because their AVO2 difference doesn't get quite as high. And then we'll just take a quick look at some data for boys and girls. Now again, the responses, if we look at the shape of the curve, increase in cardiac output for steady state exercise, heart rate, stroke volume, on and on and on, the responses look the same. But again, it's the magnitude of the values that are different. With children, as they age, we're seeing increases in most of these things, with the exception of heart rate. Maximum heart rate is decreasing as they age. That's where that equation 220 minus age to calculate maximum heart rate comes from, even though, again, it's not a very good equation, so it doesn't do a great job. But even here, you can see that the boys tend to have higher stroke volumes than the girls. They tend to have higher VO2s than the girls. And their blood pressures also go higher than the girls. So even at 10 and 15 years of age, there are differences in cardiovascular responses of boys and girls. And now we'll finish up by looking a little bit at some cardiovascular responses in blood pressure and heart rate to resistance exercise. And as you can see here, this is a double leg press using a pretty high weight, 95% of the 1 RM. They actually used an indwelling catheter, which has a pressure transducer on the end of it. You can see that during the concentric part, the MAP peaks. During the eccentric part, it drops some. Concentric back up, and so on and so forth, eccentric. But as you follow that peak along through the repetitions, in general, that MAP is getting higher and higher. And this MAP at the end is close to 350 millimeters of mercury, which is way up there. Don't forget, that means that the systolic blood pressure would be even higher. And here you can see the heart rate doing kind of a similar thing. The major increase is from rest to the first set, but heart rate continues to go up through most of the set, kind of plateaus here towards the end a little bit. And the heart rate's getting up around 150 beats per minute, which is pretty good. These data are similar, but now they're looking at systolic and diastolic blood pressures, and they're looking at 3 sets of 10 as opposed to just 1 set. Again, you can see that the blood pressure is highest at the end of the 3rd set compared to the end of the 1st set and the end of the 2nd set. Again, the other thing that you should remember is that during resistance exercise, diastolic blood pressure increases. It didn't do that during aerobic exercise. And part of the reason for that is during the resistance exercise, the muscle contractions are constricting the blood vessels, causing an increase in resistance. Remember the equation, that cardiac output is equal to MAP divided by TPR. Solve for TPR, and TPR is equal to MAP divided by Q. And so as resistance goes up, MAP will also go up. And so you see that increase going on there. And then here's a little bit of other data that looks at over here, changes in heart rate, and you can see that for set 1, 2, and 3, the heart rates got higher and higher, and they looked at different intervals. The rest interval was shorter for the open bars than it was for the gray bars, and so you can see higher heart rates. And then over here you can see blood pressures, and so you can see that there are statistically significant differences that can occur. And so resistance exercise 2, not surprisingly, causes increases in heart rates and blood pressures, and also cardiac output and stroke volume, although we aren't going to look at those data right now. And now we're going to go ahead and look at some respiration ventilation variables. Here's minute ventilation. This is for submaximal steady state exercise. And so you can see that it is submaximal steady state. Not sure what the duration is, but it is less than 35 minutes. This is pretty decent intensity, so it's moderately high, at least. VE of 100 liters per minute is a pretty good value. And so you can see that the ventilation went up really quickly, and then it went up a little bit more slowly, and then finally it hit the steady state. And that shouldn't surprise you. That's pretty typical. It doesn't look very much like what we expect to see for VO2, but it's VE, not VO2. So there's no O2 deficit and there's no EPOC, even though it looks like there could be. What is the term that's given to this increase in ventilation? Well, I hope that you're not saying hyperventilation, because that's wrong. During exercise, the increase in ventilation is called hyperpnea. And that's because the increase in ventilation matches the increase in CO2. More cellular respiration, greater production of CO2. More CO2, you've got to breathe more to get rid of it. Okay? Hyperventilation does not match the increase in CO2, and that's why you actually will blow off CO2 when you hyperventilate, and you push the PaCO2 level down, and you can hold your breath longer. And so again, you can ask Eddie and Aaron about that, and Lita, and the other people who took A&P with me, because we actually did an experiment in which we looked at the effects of hyperventilation on breath holding. Here, the data represented by the black line show you the tidal volume. And so tidal volume 2 goes up and finds a steady state, and it reaches the steady state in under 3 minutes. So that's not bad. That's about what you would expect to see. This variable, I'm not going to worry too much about it. You don't have to really understand it, but it's dead space volume to tidal volume, and it's just simply telling you that tidal volume is increasing at a greater rate than dead space volume, so this ratio goes down. That means more of the air makes it down to the gas exchange region. And then finally, the other part of minute ventilation is breathing frequency. And so now you can see that the rise in breathing frequency is a little bit more gradual. The slope of the line is a little shallower. It takes about 5 minutes before we reach steady state. A little unusual, not quite what we expect to see. And so here we can see alveolar ventilation. What is the air that makes it to that gas exchange region? And so you know that in order to get that, we need to take VE and subtract the dead space volume. And so VA will always be less than VE. These data are different than the data on the previous graph, so we can't really compare them. Intensity here looks to be a little bit less than it was in this particular graph, a little bit less. So there you go. But you know that during exercise, muscle needs more oxygen, needs more final electron acceptor. So there's also going to be an increase in O2 that's removed from the arterial blood as it passes through those systemic capillaries to the muscles. And so here you can see that increase in AVO2 difference. We're going to take more oxygen out. Resting AVO2 difference is approximately 5 milliliters of O2 taken out of 100 milliliters of blood. And you can see that that's also reflected as a decrease in the partial pressure of O2 in the venous blood. It decreases from a normal resting value of 40 down to some value below that, depending upon the exercise intensity. So this is moderate to light exercise. Okay, decreased PVO2 is actually going to result in an increased PO2 gradient as we get back into the pulmonary capillary. That's going to help the movement of O2 from the gas exchange region into the blood in the pulmonary capillary, so external respiration. The reason we see this increase in AVO2 difference is partly because of this Bohr effect. Remember that a decrease in pH and an increase in temperature shifts our oxyhemoglobin dissociation curve, which we'll look at in just a minute. Here you can see minute ventilation during prolonged exercise. And so we see, some positive drift here. This is not positive cardiovascular drift. Now it's ventilatory drift. And it's occurring a little under 40 minutes roughly. So you can see that that's the case. And interesting, here's our tidal volume. It takes a bit longer for us to reach our steady state in prolonged exercise. It's going up a little higher. Takes a little bit longer, and you can see, look at that. There's actually a little bit of negative drift here for the tidal volume. And you know that what that means is we're going to have a substantial positive drift for the breathing frequency. Now look at this response. This is kind of some crazy stuff. This gradual increase up to a little bit of a steady state, and it takes about 25 minutes to hit it now. So that's weird. That's unusual. That's one you're going to have to memorize. And then this nice, strong positive drift in breathing frequency. So you know that at the end of a hard, exhausting run, you're breathing pretty hard. And then here is, again, the alveolar ventilation. And not surprisingly, minute ventilation shows positive drift. Well, so does alveolar ventilation show a positive drift. Okay? And again, as we've already said, AVO2 difference goes up higher with higher intensity exercise, but it also starts to drift upwards. So if you exercise aerobically for greater than 35-40 minutes, AVO2 difference no longer maintains that steady state, but it starts to show this positive drift as we go up. And here we can again see decreases in the partial pressure of O2 in venous blood. We're taking more O2 out, and so the PVO2 will drop more. And here you can see that down here. Oh, PVO2, it's all over here to the left. This is resting PVO2, right about 40 millimeters of mercury. You know that the blue shaded area shows you what we would expect for a resting AVO2 difference. Here's the arterial content of oxygen at rest, about 19.5 milliliters in 100 milliliters of blood. And here is the venous content of oxygen, just slightly higher than 15. If we round off, we can just call our AVO2 difference at rest 5-ish. That's close enough. I'm happy with that. So it's 5-ish. There we go. Okay, and so this curve in the middle that you see here is our normal resting oxyhemoglobin dissociation curve. That's what we see. The blue one is the curve as it shifts due to the Bohr effect. And so here you can see it shifting downward, but also to the right. Here you can see, whoops, PVO2 at max exercise might drop down to close to 15 millimeters of mercury. That's getting really, really low. But an important point is to notice that it never drops down to 0. And it would rarely, if ever, I don't know of any data that shows it dropping down to 10 or lower. So again, this is PVO2 difference over here to the left side of the curve. And now you can see that we are indeed using the curve that shifted because of the Bohr effect. And so the blue line is showing the Bohr effect. And now we'll look at what happens if we don't shift the curve. Here's submaximal exercise. PVO2 is at 30. So it's dropped down, and you can see that the AVO2 difference has increased to just a little bit under 8 mLs per kg per minute if we use our normal resting curve. But you're exercising. pH is going to decrease, body temperature is going to go up, the curve shifts down here. And so what does that do to AVO2 difference? Oh, wow, look at that. It's actually up over 11 milliliters of O2 being taken out of every 100 milliliters of blood. So again, this does a nice job of showing you how the Bohr effect helps unload oxygen as it goes through the systemic capillaries of the muscles. And then we'll finish up. There's just a review of what we just said. And now we're going to go ahead and look quickly at incremental exercise. And so here's the VE. And as we said when we first started to talk about ventilation and respiration, the more energy you need, the higher the ventilation will be. It's not a nice straight line. There are a couple of breaks here that we won't worry too much about. That's called the ventilatory threshold. I'm not going to worry too much about those. The alveolar ventilation basically shows the same kind of response. But again, it's lower because we had to subtract out, take the dead space out of the minute ventilation, and so alveolar ventilation is always, always, always less than minute ventilation calculated at the same time. Here you can see the AVO2 difference. I should get rid of this particular graph because it shows this plateau being hit at about 60% or less of VO2 max. Doesn't really do that. These data do a better job of showing you what really happens. At about 50% VO2 max, the slope of the line flattens out a little bit, but it still continues to go up. So AVO2 difference at 100% VO2 max is greater than AVO2 difference at 75% VO2 max, even though this would suggest that that's not the case. Bad. This is just a different way of looking at the AVO2 difference. Here's the content of oxygen in the arterial blood. Here it is at rest, and here you can see it increasing just slightly as exercise intensity increases. So it creeps up a little bit. And then here is the oxygen content in the venous blood. And you can see here it is at rest, and it goes down quite a bit more as exercise intensity increases. And we actually already looked at that. And so when you look at this graph, it helps to explain this one. So here, as we go from rest to moderate exercise, we see a fairly substantial decrease in the venous oxygen content, but then it goes down more slowly. That's what's reflected here. Same thing here, but now we're also seeing adaptation. And so the major thing you see is that the maximum AVO2 difference has gone up due to aerobic exercise training. And you can see that the trained college student has a maximum AVO2 difference almost the same as the endurance athlete. Now, if the endurance athlete continues to work out for a few more months, this is going to go up more. But getting substantial change in AVO2 difference takes a long time. And so they need to keep working at it. Here's our change in partial pressure of O2 in venous blood again. And you can see that it does tend to go down more as exercise intensity increases. This would imply that the maximum it goes down is to about 20 mLs per kg. No, 20 millimeters of mercury. I'm sorry, I've done that twice. And here you can see that these data suggest that it can get down a little bit lower than 20. But suffice it to say that it drops down 20 and lower, but it still seems to stay above 10 millimeters of mercury, even when you're exercising incredibly hard. And that's at the end of this video. In the next video we're going to look at adaptations to aerobic exercise.